Okay, shall we keep going? All right, so I'm going to do the kind of second algorithm. So the first algorithm was value iteration. So we kind of focused on the value function, how we update that and improve that. Okay. Now we're going to consider one called policy iteration. So they're here, rather than starting with value function, we start with the policy, and then look at ways of updating that. Okay. So here's the kind of basic idea. So rather than giving you a, we'll get our example from before. So rather than writing down the abstract definitions and all the rest of it, so we had it's the same example as before. We've got a reward of, I don't know, 1 for being here, was it? And then it's 2 for being here. And the game ends when you either reach the 1 or the 2. Okay, and we've got our little robot friend again. Okay. 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 Right. So before what we did was we kind of took values for each of these squares and then kind of sequentially updated them. All right. In this example, what we're going to do is we, instead of starting with the value function, we'll end up with values, but what we're going to do is we start with a policy. Okay. So we just choose a fairly arbitrary policy to start with. It might be, you know, if I'm in this square, I go right. If I'm in this square, I go left. And maybe here, in these two squares, this square I go right, this square I go right, and if I'm in this square, I go left, for example. And this square, maybe I go right. Okay? So I start with the policy. Okay? And then what I do is I evaluate the policy and see what reward that's going to get me if I just run that policy over all time. Okay? So if I started in this square, okay, and I ran this policy that I've written down here for the less than rights forever, how much reward would I get from this square, from this policy? Yeah, 0. It's not going to reach the 1, it's not going to reach the 2, and it doesn't gather any reward over time, so this can be 0. Okay? And then this square, well, the same, 0. Okay? And this square? 0. And here? 0 again? No? 0. And this one? Sorry? 0? Who thinks it's 0 for this one? Who thinks it's something else? Okay, hands up. Who thinks 0? Okay, who thinks 2? Yeah, it's going to be 2, because if I ran this forever from this square, if I started here, the first thing I'm going to do is go to this square and get 2. Yeah? Alright. Alright, so we kind of look at the policy and see what happens if I run it forever. Okay? What reward will this accumulate? Okay? And then what I do is I take each square and I go, well, I'm allowed to change the first action that I do, but then afterwards I follow the policy. Okay? So, for example, if I was at this square here, I'm allowed to change the first thing that I do, but then from there afterwards I have to follow the policy as it's given here. All right? Okay, so if I'm here, what would I do for the first action? Go left, yeah? If I keep going right, okay, and then I follow this policy, I'm going to get 0, okay? But if I go left, then I get a reward of 1, okay? So I'm going to change the policy for that square from being an arrow this way to being an arrow that way. What about this guy? Well, I'm currently going left, and I get a reward of 0. Okay? And here, I'm going, if I changed it to go right and then followed the policy, I still get 0. Okay? So in some sense, there's no point in changing. Okay? So that stays like an arrow like this. Okay? What about this one? Well, if I go left and then follow the policy as before, my reward remains 0. And if I go right and follow the policy as before, it remains 0. So I might as well just stick with the same thing. Okay? Same here. If I go left and then follow the policy, then it remains 0. Okay? And if I go right and follow the policy, it remains 0. So I might as well stay the same. And the same here. Okay? And this one, I can evaluate it. If I go left and then follow the policy as before, I get 0. And if I go right and follow the policy as before, I get 2. So I might as well keep going right. Okay? So that, I did my policy evaluation, and now I've done a policy improvement step. Okay? So what do I need to do next? I need to do the policy evaluation again. I did the policy evaluation, I've done the policy improvement, now I do the policy evaluation again. Okay? So I've got a policy here that says go left if you're here, left if you're here, right if you're here, right if you're here, left if you're here, and right if you're here. Okay? So what's the value of this square now? If I ran this policy forever, what would be the value of this square? Yeah, 1, because I just go left and then I get 1. And this one? So who says 0? Put your hand up if you think 0. Put your hand up if you think 1. Put your hand up if you think 2. Okay, you're correct, 1. Okay? Because if I ran this policy forever, I go left and then I go left, and then in 2 steps I'll be done. And I get a value of 2. Okay? So notice that's a little bit different to how value iteration worked. Notice value iteration kind of propagated these 1s out. So it's sort of like as a 1, and then there's a 1, and there's a 1, and there's a 1 after each iteration. Whereas here we're kind of getting a batch of 1s. Okay? Okay, what about this square? Yeah, 0, correct, great, thanks. Because I go left, and then I'd be stuck going left and right, left and right, left and right, left and right forever. Okay? Same here. Left and right, left and right, left and right. Or right and then left and right and then left, rather. Okay? And this one? 2. Okay? So I've done 1 iteration now of the policy evaluation step. Okay? So I've done the policy evaluation, now what do I do? Yeah, we're going to do the policy improvement. Okay, so it's policy evaluate, policy improve, policy evaluate, policy improve. Okay? Okay. So, as before, I can go left or right. If I go right and then follow the policy as before, I get 1. And if I go left and follow the policy as before, I get 1. It's not much point in changing, so we just keep it the same. Okay? Notice if I apply discount factors to this, the value of this square would be slightly worse than this one. So there is a good reason for doing discount factors, though I can't be bothered doing the calculations myself. Okay? Here, okay, I'm at this square. I can change the first action that I make, but then thereafter I have to follow this policy. So here, I could go left, and then I'd get a value of 1. If I went right here, and then followed the policy, I just get stuck in this loop here, and get a value of 0. Okay? So I'm going to keep going left. Okay? Here, okay, I can go right, and then get 0 forever, or I can switch this to go left, and then I'd get a value of 1. Okay? So I want to switch to left. Okay? All right, this one. I could go left and then get a value of 0, because I can then get stuck in this infinite loop, or I could go right and then get stuck in this infinite loop. Okay? There's not much point in changing. The value's 0 either way. Okay? So for this square, it goes 0. and keeps going right. Okay, this one's a little bit different. I could go left and be stuck in this infinite loop forever, or I can change it to go right, and then I get a value of 2. So you want to change it to go right. Okay? And then this one again, I can go left, get stuck in an infinite loop with value 0, or I can go right, and I can get a value of 2. So you might as well keep going right. Okay? All right, so I've got a policy now which says if I'm on this half, I go left, and if I'm on that half, I go right. Okay? And then I do the policy evaluation step. Okay? So what's the value of being here? 1, yeah? Because you just go, this says go left. And here? 1. And here? And here? I've got a policy that says go right, right. So 2, yeah? So you have to keep in mind that this is now saying we run the policy forever. We evaluate the policy if we ran it forever. Okay? That's different to value iteration. And here would be 2, and here would be 2. Okay? All right. I can explain what's going to happen next. What's going to now start happening, and you can do this yourself at home, is we're going to start flipping these ones over. These are going to slowly start flipping over. So next iteration, this arrow will turn right, and these will stay the same. And the next iteration, this arrow will go right, and these will stay the same. And it will slowly turn these ones into 2s. Okay? All right? So this is called, this basic algorithm is called policy iteration. Okay? So there are advantages and disadvantages to both. Okay? Typically, value iteration will take more iterations. Okay? But in the policy, notice in the policy evaluation step, I need to evaluate the policy over all time. Okay? So I need to say, like, if I've taken this policy, I need to say how well is this policy going to perform if I keep doing it forever. Okay? So the policy evaluation step is a bit more expensive. Computationally, it's a bit more expensive. Okay? Whereas value iteration, the policy evaluation step, is quite a bit cheaper. Okay? On the other hand, typically you'll find that policy iteration takes less iteration. Okay? So more expensive iterations, but take less of them. Okay? Whereas value iteration, cheap iterations, so you can do many of them, but you might need to make many of them to get convergence. Okay? Another point you can make is Pullets, if we've got a finite set of actions, okay, this is going to explore that finite space of actions and then thus is guaranteed to converge to a policy, okay, an optimal policy. Whereas if we take, say, value iteration, those values might not ever converge. They'll just get, the errors will get smaller and smaller and smaller. You know, you go to like first 2 digits accuracy to first 3 digits accuracy to like, you know, first 10 digits being accurate, but they might never converge. Okay, so that's the difference. Okay, all right. So now let's give like a formal definition of the policy improvement. Sorry, policy iteration. Okay, so we're just going to sort of write down in mathematics what I've just described there on the board, on the paper there. Okay. Okay. So for policy iteration, we're going to consider a discounted program with rewards are XA and a discount factor beta. Okay. I could do this for non-discounted programming, but I don't know. It's just easier to do the proofs and things. Okay. Okay. So policy iteration, we start with a stationary policy. Okay. So that means a policy where for every state that I'm in, I've decided what action I'm going to take. Okay. And we then define a new and improved stationary policy I of pi. So now notice the iteration that I take is on the policy and not on the value function. Okay? And we do this by choosing the action for the state x that solves the following maximization. So essentially I do what I said I was doing before. I take the action that maximizes the reward over the next step plus the reward I got from the old policy. Okay? So what's that saying? I can choose any action that I like for the first step, but then afterwards I have to follow the other policy. Okay? That's exactly what we were doing before. Okay? And then what we do is we calculate the reward function of the new policy. Okay? So then I need to calculate Ri of x. Okay? So basically, we recall that this solves a certain equation. Okay? That R of x of I of pi is equal to R of x of I of pi plus beta E of x of R hat of I of pi. Okay, so where have we seen that before? So note, if we go to our, so remember when we did Markov chains, we had a way of evaluating kind of the rewards with the different for different Markov chains. Okay, now remember that when we defined a Markov chain, all you needed was the state that you're in and then some randomness. Okay, so if I've got a stationary policy, I've decided what action I'm going to take at each state. Okay, so all the information that we're using is the state that I'm in and then some randomness. Okay, so when I take a policy associated with the stationary policy, it defines a Markov chain. So then I can look at my notes on Markov chains here. Okay, and remember that I said if we've got a Markov chain, okay, I want to evaluate the kind of the rewards associated with that Markov chain. Okay, it solves this equation: R of x is equal to beta p R of x plus r little r of x. Okay. So if I've got a stationary policy, I can write down this equation, and I know that R is the solution to it. We in fact know it's a unique bounded solution to it. Okay. We also know that it satisfies certain inequalities associated with that as well. Okay? So let's think about this. Basically, it's saying that I've got some, if I think of X as being a finite set, and I can think of P here being a matrix, okay? I've essentially got a vector is equal to a matrix times a vector plus a constant vector here, okay? So if I was given the reward function, little rewards R of x, and I was given the discount factor, and I was given the transitions of the Markov chain, I can solve for R of x essentially by solving a set of equations for matrices and vectors. Okay? So what I'm sort of saying here, and we'll write this down in a minute, is that note that R of x, I'll write this down later in your notes as well, so don't worry too much about writing now. So we have that R of x is equal to I minus p, or beta p, R of x is equal to little r of x. Okay? So R of x is equal to the inverse matrix this, we've got this matrix, the identity minus beta of p, where p is the probabilities of the different transitions of the Markov chain. We take the inverse of that and apply it to the reward function. Okay? So notice, basically if I want to work out a reward function, if I want to do policy evaluation, then for policy improvement, I really need to do this matrix operation here. Okay? That's why I said it's more expensive, because if I was doing value iteration, I just do some maximizations and minimizations. Okay? Whereas if I'm doing policy improvement, I need to invert a matrix. Okay? Inverting a matrix is a bit more computationally expensive than just doing maximization. generalizations. Okay? All right. Anyway, so it's worth recalling these exercises 11, 12, and 13 from the Markov chains notes. Okay. Anyway, let's go back to where we were. So what I'm saying is, working out what r of x of pi, I of pi is here is just is basically inverting a matrix. Involves inverting a matrix. Okay. So anyway, and then, so I've got my policy. I've updated it, saying what's the best thing I can do next, given I'm going to follow the old policy there afterwards. This gives me a new policy. I work out what the reward function is for it by inverting some matrices, and then I just use that as the new policy for the next round. Okay, and I keep updating. Okay, that's sort of mathematically what we were doing before with that example. All right. And then we want to kind of decide if actually that's a good thing. So the theorem we're going to prove is basically the same thing we did for value iteration. Firstly, that under policy improvement, it improves the rewards at each step of the algorithm that you actually get a better policy that's actually going to give you higher reward. Okay. And the other thing is that, at least we'll do it for bounded programming, that this is actually going to converge to the optimal value function. Okay. So it improves things and it improves the optimal value function. Okay. It's the same again. We're proving that this algorithm actually works. Okay. So any questions about that? Okay. Okay. So we'll kind of go about doing that. So the first part we're going to show is that actually this holds. So that's equivalent to proving this, that one iteration of policy iteration gives me a better policy. Okay. And that isn't too bad. So basically, we use our exercise from before. So let me pen here. So we have the reward function for policy pi, okay, is equal to the instantaneous reward of that policy plus beta e x of pi of x of rx of pi, or rx hat of pi, I should say. Okay, that's because this is a Markov chain. Okay, so that's exercise, what was it, 11, 12, and 13 we had. So that is this statement here is 13 from the Markov chains exercises. Okay. Then, by definition, in the policy iteration, we take something that maximizes this expression. So we choose the action here. Rather than having pi of x here, we choose something that's better. Okay? Okay. So what we've got here is a policy where r of x of pi, okay, we've got some function rx of pi that says if I follow this policy, then that function satisfies an inequality here, that is less than this. Okay, I'm just going to track back to the Markov chains notes. Okay, so keep that in mind, that we've got an inequality here with R and R here for policy pi, and actually here we've got the action taken from I of pi. Okay, so the action is taken by I of pi, but the reward function's for pi. So let's just skip back to those Markov chains notes. And Markov chains notes. This says that if I follow a policy, okay, and I've got some other function that satisfies with inequality here, then I've got an inequality for the function compared to the rewards of the real function. Okay? Now, actually, we're going to use this the other way around. I'll just make a point that we can also have exactly the same lemma, but with this the other way around. Okay? So rather than having R tilde in this lemma is going to follow, we're going to basically apply this exercise 13, okay, with P being the transition probabilities of policy I of pi, and with R tilde here being the rewards from the policy pi. Okay? So I can directly apply exercise 13 here. Okay? Oh, that also means that shouldn't be a 13, that should be 11, sorry. Wait a minute. So that should be 11. Then. It's me forgetting my numbers. So that should be 11 from the Markov chains notes. And this implies, by exercise 13 of the Markov chains notes, okay, that Rx of pi, okay, I put in Rx of pi in here, and it's got an inequality when I follow the policy I of pi, must satisfy this. Okay? Okay. So that shows that every time I do policy iteration, the rewards are going to get bigger. Okay? So you're saying policy iteration is good, as in it improves the policies. Okay? So now we're going to work a little bit. So it's a little bit harder now. So that's good. So we've got that one done. But every time I apply policy iteration, I can improve the rewards. Okay? Now I need to do this part, which is to prove actually it converts to the optimal policy. Okay, and I noted when I was preparing for this lecture, this inequality is the wrong way round. It should be this way round, so typo there for everyone. That should be that way round. Okay. So here we say that the rewards from action A, beta x of A, are less than or equal to the reward function from I of pi. Okay? It's very similar to the argument from before here. Okay? So I'm just picking up, it's like a lemma, I'm just having an extra statement that's going to be useful in a minute. Okay? So why is this true? So if I look at this part, this says for any action that I choose here, I look at the reward from taking that action and then following policy pi from then on out. Okay, that's the interpretation of that equation. Okay, and I know that if I do the policy improvement, I choose the optimal action here. Okay, so that's going to definitely improve things if I replace this with the policy that I followed under policy improvement. Because the definition of policy improvement is to choose the best thing here. Okay. Now we know from the previous exercise exercise 23 above, that this is less than this. Okay? So I know that if I, rather than doing the first step according to the new policy iteration step and then following pi, if I did this and then I followed I of pi, it's going to be better. Okay? Okay? So that's saying, sorry, also in the feedback, some people noted the handwriting, so apologies for the handwriting here. It's a problem with using these tablet things. So I actually have quite neat handwriting. If it's on paper, I'm not sure. Maybe I should invest in a slightly better tablet thing. Anyway, so what have I done here? I've basically said we know that if I followed I of pi here, that improves this. And this is saying now, if I follow the improved policy for the first iteration, and then I follow the improved policy for all iterations afterwards, then that's better. Okay? But if I follow the improved policy for the first iteration and all iterations after, then this is just the reward from that policy, isn't it? Okay? So this is really just the reward, okay, from starting at state X and following the policy, the improved policy. Okay? Or alternatively, you can note that is just exercise 11 from the Markov change notes. Okay, so that's really the step from here to here, formally speaking, is exercise 11 from the Markov change notes. Okay? All right, that's going to be useful in a second. Okay? So just to recap, we're trying to show that that this improved policy improvement, the reward function with the different policies converges to the optimal reward. Okay. Okay. So one of the reasons I'm pleased to teach this course to you guys is because it is very useful to be teaching a course to people who've done a course of martingales. So we're going to use a martingale type of argument to prove the last part. Okay. So we're going to proceed to prove the final bit with the Martingale argument. Okay. Here, I'm looking at what happens if for the first S steps, I follow the optimal policy. I'm sort of assuming an optimal policy exists. If an optimal policy doesn't exist, I could take something that's within epsilon of optimal and then work with that instead. For here, I'm just assuming there's an optimal policy, so I'm a little bit cheating, but anyway. Okay. All right. So let's assume we follow the optimal policy for the first t steps, and then from there afterwards, I follow a policy pi. Okay. Okay. And we're going to assume what I'm going to show is that this term m is a super martingale. Okay? So in other words, in expectation, this guy goes down. Okay? All right. So let's show that. So I'm going to take the expectation of the difference of these two terms, so the t plus 1 term and the teeth term. And then going to condition on the filtration of the optimal policy taken at time t. Okay, so by the filtration here I mean the sets of actions and states visited by the optimal policy over t steps. Okay, and then I look at these two terms, look at the difference between the two of them. Okay, so we're going to pick up one term for this lead term here, and then we're going to pick up one of the terms from the sum in here. Okay, so you can check that this is equal to, I've realized there's some typos in the notes in the answer for this, I need to correct those, but what we're going to end up with here is the reward function here evaluated at time t plus 1. Then one of the terms, the top term from here, evaluated at time t. Okay. And then minus off one of the terms here from time to t, rather than t plus 1 here. Okay. Okay, and this is all going to be taken with filtration at time t. Okay, so I just basically looked at the two terms here, all right? Okay. So now I can do a little bit of kind of the tower property. I can look at how, given the state at time t, and given I'm taking the optimal policy at that step, we can then take the expectation of this guy for the next step. All right? So I'm just going to apply a bit of the tower property here. So the only thing that's random as far as this expectation is concerned is this e of t plus 1 here. Okay? So notice that this part here is really what we were working with in this example over here. All right, with this inequality. Okay, so it's just one instance where we've taken a policy improvement over one step, and we compare it with the expectation of this guy plus the reward from the next step. Okay, so check for yourself that I'm essentially just working with one of these guys over here. All right. Same as in exercise 24. Okay? We know from exercise 24 that this is less than or equal to 0. Okay? So this whole thing is less than or equal to 0. Okay? All right. So this martingale, or it's not a martingale, it's a super martingale, it's going down. So let t get bigger. Okay. And we can use that. So what we're sort of doing is we're interchanging between the policy iteration at time t and the optimal policy for the first t steps. Okay. So we're kind of trading off between the two. Okay. So with this, we can actually show the result that the reward function of the value iteration converges up to the optimal value. Okay. Okay, so let's do that. So it's not an easy proof, this one. I'm not sort of, it needs to be broken down into a few steps. I'll also note that where you can find a very similar proof. I kind of read this proof. So it mentioned this James Norris book on Markov chains, and they kind of go through this proof in there as well. So that's where this one comes from. So you can have a look in the kind of final chapters of that. It's the same sort of argument. Okay. So anyway, since MT is a super martingale, we know that, leaving a bit of space here, that starting from x, the value of the super martingale at time 0 has to be less than the value of the super martingale at a future time t, capital T. Okay? Where capital T is the same as the capital T in this expression here. Now you can check for yourself that the value of the martingale at time 0 means you don't do any steps according to the optimum policy. You just do steps according to the policy improvement policy at time t. Okay. Whereas the martingale evaluated at time capital T says do the first t steps according to the initial policy from your policy improvement, and then do everything else according to the optimal policy. Oh, sorry. Yeah. No, sorry, the other way around. You do everything according to the optimal policy for the first t steps, and then from thereafter you follow just the policy you started with. Apologies, just move that down there. Okay. So it's saying doing the optimal policy for t steps and then doing the policy that we started with from policy improvement is worse than doing the policy improvement step after t steps. Okay? That's what this reads as. It says, if I did the policy improvement for t steps, I've got a better policy than doing the optimal policy for t steps and then anything afterwards. Okay? So that sort of gives you a level of how much it's improved things. Okay? So then, given we're working with bounded programming and all the rest of it, I can let t go to infinity for this guy, and this guy's going to go to 0. Okay? That goes to 0 as t goes to infinity. And this guy goes to the optimal value function as t goes to infinity, the optimal policy. Okay? So this inequality says that if I let t go to infinity, the limit of the rewards from those policies is equal to the reward function from the optimal policy. v of x, okay, which is what we wanted. Okay. So we need to use a lot more about Markov chains and the kind of properties of Markov chains to do the proof that policy iteration converges. Okay. I won't discuss it at this stage, but there are things in between value iteration and policy value iteration and policy iteration. So notice that value iteration sort of looks one step ahead and then chooses a new policy and updates the values. Okay. Whereas policy iteration, remember from the picture, once we've got the new policy, we have to evaluate it over all time steps. Okay? And there are things in between. So you could do something where you take like 10 jumps and then do the policy evaluation. Okay? And there you can kind of trade off a little bit between the policy improvement, which is really great but computationally expensive, and the value iteration, which is really cheap to do the evaluation steps. Okay? But you might need to do a lot of them. Okay, so it's kind of like a fundamental trade-off between those two, and there's a bunch of policies in the middle. Okay. Anyway, let's just look at our example again, this grid world example. Okay, and again, you'll find that it calculates the correct answer. Okay. So going back to here, so here's bit of code on the grid world example as well, okay, just to show you what it kind of looks like. So we'll have the same example again with our robots, some costs and some rewards, okay. Notice I now need to use some packages for doing different bits of linear algebra, so I need to take inverses and determinants of matrices. That's because we need to do this policy evaluation part where we need to take an inverse. Okay, I define everything as before. Okay, so I define the costs on the grids, define the probability that the robot disobeys my instructions, okay, and also discount factor, okay, and then we define what happens under the different actions that I can choose, okay, and update those. And then here I explain what the bit of code here is doing. We're basically noticing that if I've got a policy, it's a reward function for a Markov chain that solves this equation. Okay, and then in order to solve that equation, I just basically need to do an inverse. All right, so that's what this does. It does the inverse part for me. Okay, so that's the policy evaluation step. Okay, and then there's a policy improvement step here. Okay, in this kind of function here. So there's two functions, main functions that are doing the work, the policy evaluation function, the policy iteration function. Sorry, policy improvement function. So the policy improvement function basically does exactly what it said. Choose the argument that maximizes the instantaneous reward given that I follow the old policy thereafter. Okay, and again, it's just some maximizations. Okay, so there's one kind of matrix inverse step which has some computation associated with it. And then there's the same sets of sort of maximizations as before. That's a value iteration. Okay? And then we start with some arbitrary policy. Okay? So notice I've said that here in the instructions, 0 is left, 1 is right, 2 is up, 3 is down. Okay? So I started with some random sets of lefts, rights, ups and downs here for the different numbers. Okay? So that's just me associating arrow with all the different states. Okay? And then I do a few iterations, and you can see, well, let's just run it all from the beginning. Okay. Notice that I didn't have to go through loads and loads of lines of code. What happened is that I updated all the arrows. Okay. I noticed that it started to say, for example, if I was near so here, it says I want to go kind of up and up for these two squares. So it's already kind of got the right answer. And then here, it's now got something very close. Well, it's actually got the optimal answer. We do one more iteration, and we find that we've got the same answer again. Okay, so Once you've done one iteration of the policy improvement, it gives you the same answer again, you've converged, you've found the optimal solution, because it's not going to increase anymore. We know when you increase the maximum, okay, then you've got the optimal policy. So once the algorithms converge, once it's fixed on its policy, you've got the optimal solution. So it only takes 4 iterations to find, well, it takes 3 iterations to find the optimal solution, and it takes 4 iterations to know it's the optimal solution. Okay? And then you just output it, and it gives you the right answer. Okay? So it's sort of quicker, like I say, it's quicker in terms of the number of iterations. It converges quicker, but it can be computationally more expensive. Okay?